Up.
I checked, and unfortunately,
I don't think it works. Oh, you know it works, no? You can hear me, no?
can you hear the speaker?
Can you hear me? He can hear me, but she cannot.
Someone in the back, can you hear the speaker? All right. We assume that it's working, so. So everyone, welcome to this afternoon session. So I'm the chair, and it's my pleasure to introduce the first speaker in this session, Professor Gerhard Rempe from Master Institute. He's going to tell us about collision experiments with trapped polyatomic molecules. Please welcome.
Yeah, first of all, thank you very much for inviting me here to the organizing committee. It's a wonderful place here. ITAMP is wonderful, Harvard is wonderful, MIT is wonderful. It's a wonderful environment, full of cold molecules. It's really great. So this is a little bit a different topic because we are not talking about diatomic molecules, but big ones. And well, big ones from my perspective. As a quantum optics person, I'm used to work with point-like particles, but these molecules that we have are already kind of a little bit larger. Anyway, this shows an experimental setup. I will give you an introduction why we do all this, but this shows an experimental setup basically of the heart of our experiment. This is an electric trap where we trap the molecules, electrically trap the molecules in this region. The molecules are guided with an electric quadrupole guide from some source. They're guided into the trap, we do the science here, and then in the end they are released from the trap into that output guide and typically detected by a mass spectrometer. So the experiment is extremely simple in terms of technology. There's at most one laser, at most one laser for cooling. And it's an infrared laser, 3 something micrometer working on the stretch mode of CH typically, or something along that line. So basically that's everything. No? I mean, everyone can build it, it's easy. So why do we do this? Why are we interested in polyatomic molecules? Well, actually, we are interested in these symmetric tops or near symmetric tops. Not all of them are really symmetric tops. Formaldehyde, for example, one of our favorite, is just a near symmetric top. But the idea is basically, and I don't have to explain to you in lengthy terms, the idea is to exploit the permanent dipole moment for long-range interactions. The nice thing about the polyatomic is typically the dipole moment is oriented along a stable rotation axis. So the dipole moment is permanent. We don't have to induce it. It's permanently there and we can exploit it, we can use it. And it's large. It's a dBi or 2 or something of that order. Well, compared to Rydberg atoms, this is of course small, no? but it's reasonably large. It has a simple, and this is one of the nice things, it has a very simple rotation and energy level structure which we can exploit for cooling. So the cooling is only done on the rotational states of the vibrational ground state. We don't go into the electronically excited state. As I said, there's only one laser involved, at most, one laser on a vibrational transition from V equals 0 to V equals 1 or so. Everything happens in the rotational manifold of the ground state. And the cooling occurs there. It has closely spaced, so these molecules have typically closely spaced parity doublets for qubit applications. I don't want to talk about that too much. It's still a little bit too far into the future. And of course, if you want to do parity violation studies or something related in chiral molecules, you need polyatomic molecules, because the chirality appears only for, at minimum, four constituents. No? Anyway, so that's a little bit the introduction. So what do we need? The experimental challenges for achieving, let's say, a collisionally dense sample is to have them cold, slow, and dense, which is not so easy to achieve, as you know. Either they are cold, maybe microkelvin, but not dense enough, or they are dense, like in the supersonic expansion. I mean, of course, it's highly dense, but not so cold, and in particular, not slow. They just go away. Microseconds time scale. We want to have them for seconds to do precision experiments, for example. So we want to have them cold, we want to have them slow, and we have them dense. And it's, of course, a combination of all this that really matters in the end, and I will give you some numbers throughout the talk. So in order to achieve this, we have developed over the last 10, 15, 20 years, almost 20 years, going back to this famous meeting here in 2004, which John already advertised. I think that's basically when we started, because we became excited in cold molecules at that time. Anyway, so we developed a kind of generic toolbox for polyatomic molecules, any kind of polyatomic molecule. We're not bound to a specific one. We can use almost any molecule by a couple of techniques which are summarized here. Electric trapping or electrostatic trapping. It's neutral molecules, of course. It's not a Paul trap or so. It's electric trapping, which we demonstrated in 2011 in the kind of trap that we are still using. We have demonstrated the Sisyphus cooling in 2012. So since 10 years or so, we are more or less routinely cooling molecules. And it's so long ago. And it became so much of a routine that I can't hardly remember how we do it. We just have one laser, that's what I remember. Anyway, I don't want to talk about the Sisyphus cooling here. And then we developed something which was also kind of important. It's a centrifuge decelerator, which goes back to some time 2014. To decelerate the molecules which come out of a cryogenic buffer gas cell with velocities of 100 or 200 meters per second. And we can use it to decelerate them to basically stand still. And we have applied these methods to a couple of molecules like water molecules or deuterated water, ammonia, formaldehyde, fluoromethane, and so on and so on. I think this is isopropanol or so, which is kind of our biggest molecule that we used in these studies. But I can't talk about everything. So this is a little bit a short introduction, so to say, what we can do in our electric trap. It's a little bit a spectroscopy, kind of precision spectroscopy experiment, which we did just for fun. Magic field spectroscopy on formaldehyde. So please remember, or let me explain to you, the electric trap that we have is basically a plate capacitor. We can apply a voltage between the plates, and that makes an electric field. There's a homogeneous field, more or less, in the plates, and a homogeneous electric field, and we can apply this homogeneous electric field to the molecules. And then in order to trap them, we have the microstructure on top of the two plates. The microstructure is plus minus plus minus plus minus. It's a multipole configuration, which gives us an exponentially decaying electric field. Magnitude-wise, it's exponentially decreasing. So it's a kind of trap where the electric field as a function of position is kind of flat in the middle, and then it has these steep walls. It's kind of box-like potential. And of course, then there's a perimeter electrode around it, and this perimeter electrode prevents that the molecules escape sideways. And then there is this input guide and the output guide here, electric quadrupole guide, where the molecules go in and where the molecule goes out. This shows actually a measured electric field distribution inside our trap, measured with the molecules. By doing spectroscopy in the trap, we can determine, so to say, the probability to have a certain electric field, and it shows a clear peak here in some normalized units. It clearly shows a peak here, and a long tail which resembles, let's say, these steep walls here, but it's orders of magnitude below the peak here. No? So it's more or less a homogeneous offset field, more or less. So what do? We try to do precision spectroscopy with that on a magic transition. What means magic? Well, there's an excited state here of the ground state, vibrational ground state manifold, J plus 1K, JK, these are the quantum numbers. And if you apply an electric field, there are positions, or not positions, there are certain values for the electric field where the slope of this state here is exactly the slope of this field. So basically, in a very good approximation, the transition frequency does not depend on the electric field. So given that the electric field is homogeneous anyway, and given that we can adjust the electric field in such a way that we can drive a magic transition like this one here, we can do precision spectroscopy for trapped molecules inside the trap. And this is demonstrated now for this particular transition here, J equals 4, K equals 3, M equals 2, to J equals 5, K equals 3, M equals 3. You don't have to remember these numbers. I can't remember myself. So it's not so important. But it's this particular transition which we investigate. And we investigate this now for different temperatures, different cooling. So we cool the molecules are loaded into the trap, they're cooled. And they're cooled to different temperatures. This is, for example, the 60 millikelvin temperature. This is a 2.6 millikelvin temperature. We probe this transition, and this transition is basically a kind of depletion spectroscopy. To detect this, we drive the molecules into an untrapped state and look how many molecules are missing. And this is, so to say, our detection signal in the mass spectrometer. Anyway, so this shows a line shape for the 60 millikelvin, and this shows a line shape for the 2.6 millikelvin. As you can see, it's a line which reduces. So this is still Doppler broadened. This is definitely Doppler broadened, but this is also Doppler broadened on this transition with a frequency of the order of 360 gigahertz. So it's a microwave transition frequency. But because this is at 300 gigahertz, 360 gigahertz, in line with this 3.8 gigahertz, we have a resolution of 10 to minus 8 or so for this particular transition here. As I said, we did it just for fun, but we tried to compare it with literature value. So this is the number that we measured here for this particular value of the electric field. 364, blah, 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 many digits, statistical uncertainty, systematic uncertainty in hertz. We can extrapolate this to the zero field frequency given the rotational constant of the formaldehyde molecule. Okay, they're available with limited accuracy, but anyway, so we can extrapolate that. And that means that in our trap, in our measurement, we arrive with this number with an uncertainty of something like 3 kilohertz. We searched the literature for maybe more precise value, but we couldn't find one. So the only one we could find, and maybe we were ignorant, I don't know. The only one we could find goes back some 40 years, 41 years here, and it has an uncertainty of 30 kilohertz. Of course, this was not done with trapped molecules. It was done in a beam of formaldehyde molecules. But we are 10 times better. Also, we are inside a trap, and also there are all these systematic effects that can happen inside a trap. But given the box-like potential, we can do this. Anyway, so this shows the potential of the trap in some sense. So let us now do further experiments, and this is collision experiments. That's the main part of my talk. Cold dipolar collisions. I changed the molecule here. It's not formaldehyde anymore. It's fluoromethane, CH3F. Why do we change it? Well, I don't know. We just picked it. It has some favorable properties, of course. Formaldehyde has also some favorable properties. But I don't want to go into the details. Anyway, so this is the experimental setup, basically. It comes with a cryogenic buffer gas cell. The molecules we are interested in, we take from a bottle, and they're cooled by collisions with helium, with a helium gas. We very much followed the approach that everyone in the community, or almost everyone, or many in the communities are using. Although this is not a pulsed ablation source, it's a continuously operated source. As I said, the molecules come out of a bottle through this tube here, they collide, and then they enter this guide. The guide is bent, which means the helium that goes out of the buffer gas cell goes straight into a pump, which is not shown here. But the molecules follow the bend here, are guided into what we call our centrifuge decelerator. It's basically a rotating disk or a rotating spiral where we bring the molecules from the periphery to the center. And by doing so, they have to climb, of course, the centrifugal potential, and that slows the molecules down. So by adjusting the speed of rotation of this thing here to the entrance velocity of the molecule, which is basically determined by the parameters of the buffer gas cell, we decelerate the molecules to some small velocity, typically 10 meters per second or maybe less, or maybe 20 meters per second of that order. And then they go through this S-piece here. This S-piece is basically a filtering because there are still some fast molecules surviving the centrifuge decelerator, but coming out at some higher speed. So these cannot follow this bend or this double bend here. They're going straight and they are lost. And only the slow ones, 10 meters per second or so, only the slow ones now enter our electrostatic trap, which is this one. Here we do the experiment. I've shown you in the first slide of my talk. I show you how it looked like. And then there's this unloading with a time of flight guide here into our quadrupole mass spectrometer. So no laser. Again, no laser, but cooled. So this is a summary. Basically, our cryogenic part here makes the cooling, but it has a boosting in it because the helium is fast. The guide we can adjust in such a way that we can determine the flux. For example, we can block the molecules from going through by having an anti-guiding piece here, adjusting the voltages in such a way that they're anti-guided or anything in the middle. So we can basically adjust the flux. The centrifuge makes the deceleration, the S-piece makes an additional velocity filtering, and then the experiment takes place here. So this is a measured distribution of molecules, the CH3F molecules, in our trap. The population in the various rotational states, please remember, they're cold, they're all in the vibrational ground state. And the highest population is in the JKM, these are the quantum numbers, 111 state. 84% probability. So it's a pretty pure sample. I'm not talking here about hyperfine states or so. No? I mean, hyperfine structure is very small for this molecule. It's closed shell molecules. So this is very small. We have tried to resolve actually the hyperfine structure in the precision experiment that I've shown you before, but we were not able to resolve it. It's just on the order of 100 hertz or so, which we have not been able to see. Anyway, so this state is mostly populated, and then there's a little bit of more population in other states like 211. So this is J equal 2, K equal 1, M equal 1, and so on with all the other states. So it's a pretty pure sample. And this is important to make when we try to make collision experiments, because the initial state distribution is pure. Now we look at the trap. So the molecules are put in the trap, and we see how many molecules are left in the trap when we unload the trap. Okay, and unloading, this is the storage time here basically in seconds, 1 second, 2 seconds, 5 seconds, some normalized signal, and we see, okay, it decays. So of course it decays, they're not trapped forever, no? I mean, it decays, but you can see that independent of the density, high density or low density, more or less, the decay is non-exponential. We've seen these kind of signals already something like 10 years ago, and we were always hoping, wow, this is collisions, it's a non-exponential decay, wonderful. But it's not. It's not, because it appears at low density as much as it appears at high density. So it's more or less density independent. And it comes from the fact that in our trap, fast molecules are more quickly lost than slow molecules. It's just a specific property of our trap. So fast molecules, for example, makes more likely Majorana transitions. They rattle around in the trap much faster, because the faster molecules are faster by definition. So they find their way out of the trap through the holes. No? They find it more easily. And so the fast molecules are left, and that makes it basically a bend curve here. And then we see basically an exponential. So this non-exponential decay is not a signature of trapping. And we were misguided for some time, and we really had to take care that we understand what's happening here. So the standard collision measurements, like looking for non-exponential decay, fails. So instead we do the following experiment. The strategy is to operate the electric trap like a test tube in chemistry experiment. So we have a trap, we fill a sample in, we fill another sample in and see what happens. Okay, that's the whole idea. So how do we do this? Three distinct experiments, that's what we do. And then we compare the results. We have a sample A experiment where we just load the trap for, let's say, 2 seconds, and then it decays and we measure what comes out. We have a sample B experiment. We load it later. We just load it, let's say, for a second, and then it decays, and we measure the decay. And then we do the two together, sample A and sample B together, give sample A plus B, and then we see a signature. Basically a signature like this, and we are interested in N, or this part, how many molecules come out. And we compare this part, the integrated part here, we compare this with the integrated part here, plus the integrated part there. So our collision signal is supposed to be delta N, is Na plus Nb minus Na plus B. That's the idea. I mean, this is a pretty straightforward idea. This is a little bit a result. So this is a density as a function of time. So this is the A sample, it just decays, so it was loaded and it decays. This is a B sample, the blue one. We wait a little bit here to let transient, we're switching the voltages and many things happen, so I don't want to go into the details here, but we wait a little bit, 100 milliseconds or so, and we load it, and of course it increases. And this is the N plus A. Sorry, A plus B experiment. No? This is the first experiment, this is the second experiment, this is the third. Again, this is a collision signal. So now we plot the collision signal, delta N, as a function of N, or N squared. The first thing that you can note is that the delta N here is much smaller than N. Please remember the N was something like 10 to 7 per cubic centimeter in our trap, loaded by this efficient centrifuge deceleration. So the initial density was something like 10 to 7, and the delta N that we see is a few times 10 to 5. So the signal is small, a few percent or so. And then as a function of the density squared, this is how we define it, it increases more or less linearly. And it increases linearly for 2 different voltages that we apply as a homogeneous offset field between the 2 capacitor plates, 0.5 kilovolts and 2.4 kilovolts. And this is for a whole time an integration time of something like 1 second. Again, still, this is the collision signal of how we defined it, and we see a clear functional behavior of N squared. So this is a signature of collisions. And it's a signature of collisions for different electric field, so it shows an electric field dependence. So how can we understand this? How can we deduce, let's say, rate constants from this? Well, this is the equation of motion, basically. The density changes because there is some loading mechanism here from the centrifuge. There's some loading, there's a loss of the atoms of the molecules from the trap, sorry. And there's this collision signal. So given this equation for the A sample, for the B sample, for the A plus B sample, we can derive an equation of motion for the difference, no? The signal we are interested in. And it's given basically by this here. The delta N squared we can more or less forget because the delta N was small compared to N, so we can forget about this term. So we're only left basically with an equation, a differential equation which has measured parameters like NA and NB, and an unknown parameter K, which is a two-body collision constant. And this we can extract from a fit of this function, of this differential equation, to the measured data. And here's the result. So this is the delta N measured, the experiment, and calculated according to this differential equation I showed you before. And it agrees pretty well, provided that we fit K to 2 times 10 to the minus 8 cubic centimeter per second. So that's how we determine the rate constant. Okay? And it agrees pretty nicely with the experiment. Okay, I would say. So as I already mentioned, it depends on electric field. That shows the experiment. So we do the same experiment for 2 different values of the electric field. Again, this 0.5 kilovolt per centimeter and 2.4 kilovolt per centimeter. And the K we deduce, one I've already shown you, the 2 times 10 to minus 8 in some units here. And then at a different voltage, like a smaller voltage, it's almost 4 times that number. So the rate constant depends. So the rate constant depends on electric field, first of all, and second, it's independent of the density, as it should be, because the rate constant is just a constant. It's a typical parameter for the molecule. But the molecule apparently reacts to the change in the electric field. So the interpretation that we have now in mind is this one. So there is a collision. So this is the initial state. It's a 1-1 state. There's one low field seeking state, which is trappable. And these 2 states are not trappable in our trap. So they come aligned in this state. There's a collision partner here. And then what happens during the collision process, it's just dipolar relaxation. Dipolar relaxation, which allows to populate all the 3 states here. But this state is still trapped, and this state is not trapped, and this state is also not trapped. So we have losses. Okay? So the physical mechanism behind everything that I described to you is this dipolar relaxation, which we model now. There's a long model. I don't want to go into the details. There's a long model. We calculate what we would expect for this mechanism, and this gives a theory curve. The K as a function of the electric field, this homogeneous offset field, and the black is the theory. Yeah, it decays. So higher electric fields stabilize the dipoles. So the dipolar relaxation goes down. And the red one is the measured data. And it agrees almost perfectly well with what we predict, or with what the simulation predicts. So from this very nice agreement, we conclude basically that what we see in our experiment is more or less 95% dipolar relaxation. So let me summarize. We calculate the elastic collision. Okay, there are also elastic collisions. The elastic collision which can lead to loss because the molecules might have different velocities, and after the collision, one molecule might escape the trap because the kinetic energy is too large. We calculate this and we come with a rate constant. We calculate a rate constant of that order here. 4.5 times 10 to the minus 11, much smaller than that for dipolar relaxation. So we can forget about this. We calculated the Langevin rate constant. Not a very precise theory, but we tried to calculate this, and it comes also with a number which is too small to fit with the observation. So from this we conclude that 95% of our losses we can attribute to this dipolar relaxation. This is just maybe some numbers here for the cross-section, for elastic collisions and the dipolar relaxation. So we come up with cross-sections of something like 10 to the minus 11 square centimeters. So large cross-sections because of this long-range dipole-dipole interaction. So I think this is my second to last slide. basically a summary of what we've seen. Molecule-molecule interaction are fully captured in our experiment, are fully captured by this long-range dipole-dipole interaction. Some of you might remember that a couple of years ago we did a first collision experiment with the same kind of molecules, but at that time we were not able to observe the dipole-dipole collision. This was basically all elastic collisions leading to losses some years ago. But this experiment shows that we are able to see in full beauty, if you like, the dipole-dipole collisions. Anyway, so what we would like to do in the future is cool the molecules further. This was 350 millikelvin, so they were not really that cold. Well, they were cold, but not ultra cold. We would like to cool further. That would increase the elastic dipole-dipole cross-section and decrease the dipolar relaxation rate because they're just slower. No? They're just slower. They're more stable, and maybe that can allow us to reach a regime where we can actually see some rethermalization or so, which we have not been able to see so far. We looked into this, but we have not been able to see it. Anyway, so this is my last slide. It shows a picture of the team with Martin Ibrügger, Florian Jung, Alex Brehn, Isabel Rabe, Martin Seppenfeld, Jindara Matzo Prampao. This is Thai. I can't pronounce this. and Manuel Koller. It was a wonderful team. We had fun, and this was fun giving the talk, and I hope you had some fun as well. Thank you very much. Okay, as I said, there are for example, the trap has this multiple configuration. So the electric field minima in the vicinity of the steep walls. But we try, by design, make the electric field adiabatically rotate without going through zero by shaping the microstructures in a trapeze-like form. That gives us a non-zero electric field, but still there's a minimum. So the molecule that goes through can make a Majorana spin flip and leave the trap. Otherwise, the molecules are just slow and they are aligned in the electric field, which is strong. And I've shown you the lifetime. The lifetime is seconds, many seconds. And it's not density dependent. And we see a clear density dependent effect. So I would not support the idea that that part of our results can be interpreted as a flip in the orientation of the molecule. You see what I mean?
It's, I guess, naively a bit surprising that the dipolar relaxation rate should decrease as the electric field increases. Do you have a simple picture for us?
I think it stabilizes. The energy level splitting becomes larger and larger. It stabilizes the orientation of the molecule. That's my naive interpretation. I mean, the idea, of course, would be, we see this decrease, no? Go to higher values of the electric field. And then dipolar relaxation goes to very small values. But we need to go to really high electric fields. We tried with this trap, but we destroyed it because it gave sparks. So now we are building a new trap, which hopefully we can have a larger electric field. Well, intuitive interpretation, yeah, I mean.
Yeah, well, first, somebody up there had a question that you probably can't see. Maybe then you can come back to me.
All right, so that wasn't your question. Do you have a question?
I do, but yeah.
Okay, let's begin.
Thank you. Thanks for the talk. I was curious about the last picture that you showed. About
This one?
You show the data for there's experiment points and the calculated actually the fit theory. Yeah, the second.
This one?
This one, yes. It seems that the experiment seems to show a different trend that is have some like a systematic deviation from the fit. I wonder, like, does it tell us like other things about, like, for example, three-body collisions? Like, is there any other process that's happening?
You mean the theory is a little bit steeper than the experiment? It's down, it's lower, it's below the theory here, and it's maybe above theory there.
Yes.
You're thinking about three-body collisions. I cannot exclude it, of course, but I wouldn't say that this probably doesn't play much of a role because the two-body collision signal is already small. So I'm not so convinced that three-body should play a role here. But I cannot exclude it, of course. No, I don't have a real explanation why there seems to be a little bit of a systematic here. But please keep in mind also, I mean, our density calibration is maybe not extremely perfect. No? We measure with a mass spectrometer, which has an efficiency which is very small. We try to calculate, we try to characterize it as good as we can.
We have time for one more question, and maybe that will be David.
Yeah, thanks.
Sorry.
So I guess maybe responding to Mike's question a little bit. So when I was imagining what this dipolar relaxation looks like, if I'm sitting in the rest frame of the molecule that you're probing, and I see the collision collision partner fly by,
Yeah.
basically what I see is a pulse of electric field.
Yes.
And, you know, the closer you are, the stronger that field is, but also the shorter it is in time, and therefore the broader the frequency content. Because you have a pulse of electric
And that
field
can flip.
before you transform it. So whatever's, you know, part of that Fourier spectrum is close enough to resonance will flip you, and that, I think that gives the right kind of scaling with.
It's a kind of Heisenberg uncertainty or energy time uncertainty argument.
Yeah, exactly.
Okay, shouldn't it go small as the electric field goes to zero? At least here it just seems to go up and up and up.
Yeah, it goes up.
And does your, if you continue your model to zero, does it eventually turn around and come down?
I don't know. I mean, we were desperate. We were desperately trying to go into this direction, but not so much. But I agree. Maybe we could have done more measurements down here, because this is where the collision signal becomes larger, no?
All right, so let's.
Okay.